Hey everyone, thank you for joining me for another test review. Today we're going to be looking at the Trig Identities test review. So let's get right into it. First thing is, I listed 3 things that you just have to know cold. You have to know your trig identities. You have to know your unit circle. You have to know how to solve equations. If you can do these things, then you're going to be able to get through the test pretty good. Now, if you're missing one of these, or if you're missing more than one of these, you're going to have some struggles when it comes to this test. So let's start here. Number 1, simplify this. Now, when I look at this, I want to say like, okay, everything can be written in terms of sine and cosine. So like secant, I can write that as 1 over cosine of theta. Sine is already sine of theta. Now cotangent, I can write as cosine theta over sine theta. And cosecant, I can write as 1 over sine theta. Now look here what happens. Well, this sine theta cancels out with this sine theta, and this cosine theta divides out with this cosine theta. So everything that's left, well, 1 times 1, that's still going to be 1. So everything that's left from here is 1 over sine theta. Whoops, I actually meant to put that in blue. There we go. So now I have 1 over sine theta, but that's not as simplified as it can get because I still have this fraction here. So let's use the reciprocal function for 1 over sine theta. Well, that's just equal to cosecant of theta. So that's going to be all of that simplified into cosecant theta. Number 2, when you have, let me rewrite this. When you have a couple of fractions without common denominators, oops, that's a 1. When you have a couple of fractions without a common denominator, you're going to want to create a common denominator. So like over here, what's missing is cosine x. So I want to multiply by cosine x over cosine x. And then on the second fraction here, I'm going to multiply by sine x over sine x, because that's what's missing. And if you notice here in our denominators, I have cosine sine and cosine sine. So that's going to create a common denominator. So I'm going to multiply here cosine x times tangent x, just like that. And then 1 times sine is going to be 1, or just sine x. And then that denominator is the same, cosine x times sine x. Well, now let's look at what we have here. Well, cosine times tangent. Let me write this part, just that part over here, cosine times tangent. So cosine times tangent, but tangent I'm going to rewrite as sine x over cosine x, that quotient identity. So those two divide out, and what's left from here is sine x plus sine x divided by cosine x sine x. Well, in this numerator I have sine of x plus sine of x. So if I have 2 sine x in the numerator, so 2 sine of x's divided by cosine x times sine of x. Now what you might notice is that sine of x divided by sine of x, that's going to get us 1. So those two are going to divide out. And now I have this is equal to 2 over cosine of x. But again, we have this fraction in the end, so we're going to want to write it using the reciprocal identity. 2 over cosine x is going to be 2 secant x. And that is going to be our simplified version of the expression. All right, moving on now to question number 3. If x is pi on 3, we need to find sine of x plus pi. Now there's not much going on here, so let's actually just, I know that x is going to be pi on 3, so let's substitute that in. Sine of pi over 3 plus pi. And then let's see, if I wanted to add these, well, that's going to be equal to like 3 pi over 3. This pi is equal to that. So if I wanted to add these, I can have sine of, well, 3 pi plus 1 pi. That's going to get me 4 pi over 3. Well, what is 4 pi over 3? So on the unit circle, sorry for this awful unit circle, let's see, pi over 3 is over here. then we have 2 pi over 3, 3 pi over 3, and then 4 pi over 3 right there. And we want the sine value, but let's get the coordinate down. Well, the coordinate down for that is going to be negative 1/2, comma, negative square root of 3 over 2. So if I want sine, my sine are the y values, so this is going to be my answer. Sine of 4 pi over 3 is just equal to negative square root of 3 over 2. And that's how you want to do this one. All right, another problem here that we have, cosine of theta is equal to 4 over 5. We need to find 1 over sine pi over 2 minus theta. Well, sine of pi over 2 minus theta, well, that's convenient because this is a cofunction identity. Well, what does that cofunction identity equal? Well, 1 over cosine of theta. Well, 1 over cosine of theta, we know that cosine of theta is 4 over 5. So I can substitute that in, 1 over 4 divided by 5. And then if I just want to get that reciprocal, 1 divided by 4/5 is just a reciprocal, so 5 divided by 4. So this right here, actually don't circle it, this right here, this 5 over 4 is equivalent to 1 over sine of pi over 2 minus theta. Now we want to solve for this equation on the interval from 0 to 2 pi. Again, that's the interval that we've been solving everything on the interval 0 to 2 pi, including 0 but not including 2 pi. So what I have here is basically I just want to isolate this trig function. So if I subtract 2 on both sides, I'll have cosecant x is equal to negative 2. And then I want to solve for x, so I want to take the inverse cosecant. So the inverse cosecant of negative 2. So let's think about this. When is cosecant? Well, cosecant is equal to 1 over sine, or 1 over the y value. So again, thinking back to the unit circle. So my y values need to be equal to, well, what's going to get me 1 over y? Well, that's when y is equal to negative 1/2. So I need to think about when are the sine values on the unit circle equal to negative 1/2? Well, negative 1/2. Well, let's just think in this first quadrant here. When is it going to be equal to? When is this going to be equal to? When are the y values equal to negative 1/2? Well, that's at right there at pi over 6. But this is positive 1/2. Both of these two are positive 1/2. So if we want the negative 1/2, it's going to be right there and right there. So this angle, so this is 6 pi over 6. This is x is going to be equal to 7 pi over 6. Or it could be equal to, well, this is 12 pi over 6. So this is going to be 11 pi over 6. And that'll be the two solutions that we could possibly have for x. Next, we want to just see which of these answers, which of these 4 answers is not going to be equivalent to cosecant of theta. So this is where you really have to know your identities. So if you have trouble remembering your identities, that's where this little hexagon thing came in. And this is going to be tangent, sine, cosine, cotangent, cosecant, and secant. So if I have secant of 90 degrees minus theta, well, that is that cofunction identity, and that is equal to cosecant. So we know that is equal to cosecant theta, so we don't really need that. Well then, this one, at the square root and I see something squared, I'm going to want to be thinking of a cofunction, or sorry, not a cofunction, a Pythagorean identity. So that's where you had kind of like this triangle happening here. Well, that triangle said 1 plus cotangent squared is equal to cosecant squared theta. Forgot the theta over there. All right. And if I wanted to solve for cosecant, I would take the square root of both sides and end up with 1 plus cotangent squared theta is equal to cosecant of theta, which also works out. 1 over sine theta, well, that's just a reciprocal identity for cosecant, so that works out. Well, let's look at this. 1 over sine of pi over 2 minus theta. Well, that is that cofunction identity over here, so it ends up being 1 over cosine theta. Well, 1 over cosine theta is equal to secant theta. And secant theta is not what we're trying to get. We're trying to get to cosecant theta. So this D right here, that's going to be the answer to this question, because this one is not equal to cosecant of theta. Another simplified question. Let's go ahead and distribute those functions to each other. So cosecant of theta times sine theta, let's put that next to each other. So cosecant of theta times sine theta, and then cosecant times cosine. Let's see what we get with that. So plus cosecant theta times cosine theta. Well, let's write everything in terms of sine and cosine. So cosecant theta, well, that's 1 over sine. So I end up with sine theta over sine of theta plus cosine of theta, and cosecant again goes into my denominator as sine theta using a reciprocal identity. Well, what you might notice is sine divided by sine, those divide out, we get 1. So I get 1 plus, and cosine over sine, that's a quotient identity. Cosine over sine, what is that? That's cotangent of theta. So this right here is going to be the simplified version of our function up there, that expression. All right, so I have another one. This one looks like it'll be a little bit longer, so let's start working through it. You have to know how to simplify. You have to know all these identities. You have to know how to square things. So as I go through this, let's kind of like work through it quickly. Let's see what happens. So I have sine of theta plus cosine of theta squared. So if I square that, that's going to be sine squared theta, square the first, take the first times the last and multiply that by 2. So plus 2 sine theta cosine theta. And then square the last, so plus cosine squared theta. And I haven't done anything with that denominator, so I just need to bring it down. 1 plus 2 sine theta times cosine of theta. Well, what I notice here is anytime I have sine squared of theta plus cosine squared of theta, I could rearrange this. I can rearrange this. Let me actually go ahead and rearrange what we have here. So if I could put sine squared theta plus cosine squared theta plus 2 sine theta cosine theta divided by, let's not do anything with that denominator right now, 2 sine theta cosine theta. Well, what I notice is this sine squared plus cosine squared. That is a Pythagorean identity. That is equal to 1. So let's make that substitution. Let's say that that is equal to 1. So that's going to be equal to 1. So sine squared plus cosine squared, that's a 1 plus 2 sine theta cosine theta divided by 1 plus 2 sine theta cosine theta. Well, those two are the exact same. So anytime I divide by the exact same thing, they divide out, they divide and equal 1. And that is a simplified version of the expression that we had above. All of that boils down to just be 1. Here I have another equation that I need to solve for on the interval from 0 to 2 pi. And what I notice here is basically this is in quadratic form. I have something squared, and then I still have the same trig function. Both of them are cosine. So let's see if this can be factored. So there's no leading coefficient, just 1 right there. So then 1 times 1, I'm going to get 1. And I need to find a couple factors of 1 that combine to be 2. Well, that's going to be 1 and 1. So positive 1 plus 1 is equal to 2. So let's see what I can do. Those are going to be my factors. So cosine of x plus 1. And then cosine of x plus 1 is equal to 0. Now, whenever I have two factors, and if you don't believe that these are going to be the factors, go ahead and multiply them out. First, outside, inside, last. And double check that you do get what we started with up here. Along with my notes, I know like this is going to work out, and I can, anytime I have something multiplied by itself, like I do here, cosine x plus 1 times cosine x plus 1, well, that means that it's squared. So cosine of x plus 1 quantity squared is equal to 0. And now this makes it very simple to solve. I could get straight down into it. I could take that square root of both sides. Those two cancel out. So now I have cosine of x plus 1 is equal, well, the square root of 0 is just 0. And then I could subtract 1. Subtract 1 there, subtract 1 here. So those cancel, and I'm left with cosine of x equal to 0 minus 1, which is -1. So again, we want to think back to the unit circle. The unit circle says, when is cosine? Well, cosine going to be my x values. Okay, so when is cosine going to be -1? And this is a unit circle on the Cartesian plane. -1 is happening over here. Well, what is that angle? That angle is pi. So -1, 0 is the coordinate. So again, we wanted that x value for cosine. So my x is equal to the angle that we're looking for. X is equal to pi for our solution. Cosecant of x is equal to -3, and tangent is less than 0, or what you want to say immediately think about, it's negative. We want to determine secant of x. So the way we're kind of doing this is using that hexagon again. And so we had tangent, sine, cosine, cotangent, cosecant, and secant. So using that as a good starting point, I know that cosecant is -3, and I know that tangent is negative something, but we want to determine what is secant. What is going to give us secant of x? So what I start to immediately think of is a Pythagorean identity. If I'm only given really one piece of information, I'm going to use a Pythagorean identity, and that identity says 1 plus cotangent squared theta is equal to cosecant squared theta. Well, I know one of those pieces of information. I know cosecant is -3. So let's make that substitution. 1 plus cotangent squared theta is equal to -3 parentheses squared. Well, let's go ahead and solve for this. I have cotangent squared theta equal to, well, 1 plus cotangent squared theta equal to 9. Subtract 1 on both sides, and I'm going to get cotangent squared theta is equal to 8. And if I want to figure out what cotangent is, I still just need to take that square root. So cotangent of theta is equal to the positive or negative, and we'll figure out which one in a second, the positive or negative square root of 8. Well, the square root of 8 can be split up into the square root of 4 and the square root of 2, and we know the square root of 4. So we know the square root of 4 is 2, and then we still have the square root of 2. So it all boils down to be one of these plus or minus 2 square root of 2 is cotangent of theta. Well, why did we go into all of this process to find cotangent? Like, why did I do everything to find cotangent if what we needed was secant? And maybe there's an easier way to get to this, but this is what I'm thinking about. And so what I'm going to do here is, all right, so I have plus or minus 2 square root of 2. And I need to determine, is this going to be positive or negative? Well, cotangent is the reciprocal of tangent. They need to have the same sign. So since it's negative, I know that cotangent is negative. So let me fill this in, negative 2 square root of 2. And now I can find tangent over here. Actually, maybe there's a better way to do this if I could just go and use that quotient identity. I know that cotangent of theta is equal to cosecant over secant theta. And that's just, cotangent's equal to the quotient of the next two. And there's probably other ways we could go about this, but this is the first one that's popping up into my head. And let's make the substitutions that we know. I know that cotangent is negative 2 square root of 2. And that we need to solve for secant, but cosecant is negative 3 divided by secant theta. So if I just need to solve for secant, let's multiply by secant theta times negative 2 square root of 2 is equal to negative 3. And I can divide both sides by negative 2 square root of 2. Well, those divide out, and I'm left with secant of theta, which is what we need to solve for, those negatives divide out, so those both become positive. So 3 over 2 square root of 2. And what I want to do with this is I have this radical in my denominator, so I want to rationalize the denominator, so multiply by square root of 2 over the square root of 2. And we're going to have secant of theta is equal to 3 square root of 2 divided by, 2, and the square root of 2 times the square root of 2 is 2, so I have 2 times 2, which is 4. So secant of theta is 3 square root of 2 divided by 4. So 3 square root of 2 divided by 4. And there might be other ways to go through this problem. There might be I don't know all the different methods that we can get to this. Like, we could use a Pythagorean identity. We could solve for any of these other functions and use reciprocal identities. Like, there's a ton of different ways that we could get to this answer. However, this is the only one that could pop into my head at this time. So if you think of another way to do it, that's great. Going to be just a regular kind of definition question. What is the shape of a sine and cosine function called? You guys might remember this from our last test. This was the exact same question on the last test, and I've told us this in class, but it is called a sinusoid, and that is a squiggly shape. That is a sinusoid. These two given values to evaluate all 6 of our trig functions. So this, again, we want to use kind of like that hexagon to help us put everything together. Here's tangent, sine, cosine, cotangent, cosecant, and secant. The first thing I notice here is I have cosine of negative x. Well, cosine is an even function, so that negative x really doesn't mean anything. So I can just have cosine of x is equal to 1/2. Now this is different than odd functions where it would kind of like come out here, but this is not an odd function, so we don't have to do that. So cosine of x immediately is 1/2. Well, how am I going to get anything else? Well, there are a couple ways I could go about this. But the first way that I think about is I can use a Pythagorean identity. I know that sine squared of theta, I guess I should use x here. So I know that sine squared of x plus cosine squared of x is equal to 1. So let's make the substitution that I have. Sine squared of x plus 1 over 2 squared is equal to 1. And we could just go along and solve. Just all we have to do is solve for sine of x. So sine squared of x is equal to, plus 1/4 is equal to 1. And then we just need to subtract 1/4 on both sides. So sine squared of x is equal to, 1 minus 1/4 is 3/4. And then we just need to take the square root the square root of both sides. So sine x is equal to the positive or negative. Well, the square root of 3 is the square root of 3, and the square root of 4 is 2. And then we kind of run into this problem of which one is it, positive or negative? And this is where we get some information. All right, so we know that tangent is going to be negative, okay? And then it's equal to sine over cosine. Well, we know that cosine, well, 1/2 is a positive number, so I know that this is a positive number here. Well, since I know that this is positive and I know that tangent's negative, the only thing that leaves for sine is a negative value. So I know that sine needs to be negative square root of 3 over 2. So sine is negative square root of 3 over 2. Well, moving forward, the secant is going to be the reciprocal of cosine, so all I have to do is flip this, so 2 over 1 or just 2. And then cosecant is going to be the reciprocal of sine, so I just need to flip negative square root of 3 over 2, so negative 2 over square root of 3. Except here, I have to rationalize the denominator, so multiply that by the square root of 3 over the square root of 3. Well, what do we get from this? Well, I'm going to get negative 2 square root of 3 divided by 3. So square root of 3 times square root of 3 is 3, and that's going to get us cosecant. Negative 2 square root of 3 divided by 3. Well, how am I going to get tangent and cotangent? Well, that's not really going to be too big a deal because I can use product identities. And this is really the only spot where I use product identities to kind of figure out all the 6 trig functions given just a little bit of information. So sine times secant, so negative square root of 3 over 2 times 2. Well, those 2's divide out and I'm left with just negative square root of 3. So tangent is negative square root of 3. And cotangent, I can multiply those two. Cotangent, I can multiply cosine and cosecant and get 1/2 times negative 2 square root of 3 over 3. Well, those 2's divide out, and I'm left with just the negative square root of 3 over 3 for cotangent. So negative square root of 3 over 3. And that's all you really need to show on your test, is that you have all 6 of the trig functions. You don't really need to list them out. If you make a little hexagon there, that's going to be enough information for me. I know like this is a way that we've labeled it in class. Function that we need to solve for, another equation that we need to solve for. So what I noticed right off the bat is that if I could combine these sine of x. So I have 6 sine of x over here and 4 sine of x over here. So let's combine those. So minus 4 sine x on the right and minus 4 sine x on the left side of the equation. So 2 sine x plus 3 is equal to 2. And what I want to do is I want to continue isolating the sine of x. So subtract 3 on both sides, and I'm going to get 2 sine x is equal to negative 1. And then I can divide by 2. So sine x is equal to negative 1/2. Well, now we need to just think about the unit circle again. I know this is coming up a lot. So there's the unit circle, and we need to figure out when the y value is going to be negative 1/2. Well, that's at pi over 6. Well, this is actually, pi over 6 is square root of 3 over 2 comma 1/2. So it's a positive. So here's sine. It's a positive 1/2. Well, in order to get the negative 1/2, I'm going to have to come down here to below the x-axis. So my x values, the answers to this equation, are going to be, well, what is this one? This one is going to be, let's see, this is 6 pi over 6, so 7 pi over 6. Or we could have this one over here. Again, we're pretty much assuming we're on the interval 0 to 2 pi. But 7 pi over 6, and then this one is going to be 11 pi over 6. By this identity. Remember, for verifying, you cannot work on both sides of the equation. So don't try to like multiply both sides by secant of x plus 1. You can only pick one side and only work on that side and try to make it match. So Here, I think that the left side is more complicated and it's easier to simplify things. It's tougher to make things more complicated. So we're going to take tangent of x over secant of x. And what you want to remember from this when we're simplifying these and getting rid of the denominator is you're going to multiply by the reciprocal. So secant x minus 1 divided by secant x minus 1. Well, tangent times secant of x, that's going to get me tangent secant. Tangent x, secant x. And then tangent times negative 1 is minus tangent of x. Let's see what happens here. In my denominator, I'm going to have secant times secant. That's going to be secant squared x. And then the outer and the inner are going to cancel out because they're conjugates. So 1 times negative 1 is going to be minus 1. Well, this, anytime I see like something squared and then plus or minus 1, I immediately think of a Pythagorean identity. I'm not exactly sure which one it is. So let's write out the most basic Pythagorean identity. And I need secant. So what's going to get me secant? Well, 1 over cosine gets me secant. So let's see. If I divide all of these by cosine squared, well, I'm going to get, well, sine squared over cosine squared, that's cotangent squared. Wait, no, that's a lie. It's not cotangent squared. That's going to get me tangent squared x. Well, cosine divided by cosine, that's 1. And then 1 over cosine squared is secant squared x. Well, if I subtract 1 over here, so it's going to be minus 1 and minus 1. Well, secant squared x minus 1 is equal to tangent squared x. So let's make that substitution. So tangent of x, secant of x, minus tangent of x, divided by secant squared x minus 1 is tangent squared x. So let's look at this. I have tangent of x, secant of x, minus tangent of x on tangent squared x. Well, let's come back up to the numerator because I did distribute a tangent of x, but I can factor that out now. So factoring this out, I can get secant x minus 1 divided by tangent squared x. Well, what happens with this, tangent x divided by tangent squared, I'm just going to be left with secant x minus 1 divided by tangent of x when I simplify those. And then what else? What else can we do? The secant x minus 1 divided by the tangent of x. Well, then that's going to be, let's see, what can I do with that? Well, I can write this over everything. Actually, no, what I want to do is use my reciprocal identity. So secant x minus 1 times cotangent x. The reciprocal tangent is cotangent, and I want to distribute that. So secant x cotangent x minus cotangent x. And what I notice here, this minus cotangent x is matching on that. Well, let's see, what else can I do? I can write the secant x and cotangent x in terms of sine and cosine. Well, secant x is 1 over cosine, and cotangent is cosine x over sine x minus cotangent of x. Well, those cosines divide out, and I'm left with 1 over sine. And 1 over sine is a reciprocal identity, the reciprocal identity cosecant x. So I have cosecant x now minus cotangent x. And that's exactly, and that is going to be my proof. Everything that we've written here, that verifies that that tangent x over secant x plus 1 is equal to, it's equivalent to cosecant x minus cotangent x. Now, I know in class that when we were verifying the identities, you want to put in all your reasoning, and I kind of left that off here, but you're going to want to provide all your reasoning in some way. So like right here, this is the conjugate, and then here we distributed, so we distributed everything right there, and you're going to want to put in everything that you have. So let's see, right here I have, what do we do there? Oh, this was a Pythagorean identity. You can abbreviate. Pythag is good enough. And then here we factored, but we wouldn't have had a factor if we didn't distribute, and that's fine. And then after we factored, we simplified again. So just simplify. And then after we simplified, I used a reciprocal identity, right? Because tangent of x came up and that became cotangent. So reciprocal, or recip. And then we distributed again. And you're going to want to provide all these explanations, all of these reasons, and very quickly, just so I can identify what you're doing. And then we used, let's see, this was a reciprocal identity and a quotient identity. And then what we did from there is just simplify, and we got it. So this is how your verification should look. Cosecant x minus cotangent of x equal to 1 on the interval from 0 to 2 pi. So when I do this, there's really nothing I can do. I can't write this 1 over sine minus cosine over sine. I guess I could, but it's not really going to help me simplify anything. So what I'm going to do is add cotangent x to the other side. And for some people who remember this, we're going to be squaring both sides. So you're going to want to definitely be very quick with this. So if I square both sides, I want to get cosecant squared x is equal to 1 plus the first times the last multiplied by 2. So 2 cotangent x, and then square the last. So plus cotangent squared x. And then we're going to want to use a reciprocal, not a reciprocal identity, a Pythagorean identity for cosecant squared. But I don't exactly remember what cosecant squared is. So I'm going to write out my basic identity. And I'm going to divide this by sine squared, because 1 over sine squared gets me cosecant squared. So divide everything by sine squared. That's what tells me what I need to divide everything by. So I get 1 plus cotangent squared x is equal to cosecant squared x. So I can make this substitution. 1 plus cotangent squared x is equal to 1 plus 2 cotangent x plus cotangent squared x. Well, let's see what happens here. I can subtract 1. Let's subtract 1. And then I can subtract cotangent squared x. Well, everything ends up canceling out. So I'm left with 0 equals 2 cotangent x. And then I could divide both sides by 2 to solve for x. So 0 is equal to cotangent x. And when is cotangent x equal to 0? So thinking back to that unit circle, cotangent of x is 0 when x is equal to, well, cotangent is cosine over sine. So when cosine is 0, that's going to be at pi over 2 and 3 pi over 2. Well, whenever you square both sides of a function, you run into the issue of possibly creating extraneous solutions. So you're going to want to check your solutions and see if anything comes out to be extraneous. So let's see, cosecant of pi over 2 minus cotangent of pi over 2, is that equal to, little question mark, is that equal to 1? Well, let's think about this. Cosecant of pi over 2, that's 1 over y, and the y value is 1, so I end up with 1, minus cotangent of pi over 2, that's 0, so does that equal 1? Yes, it does. So pi over 2 checks out. Now let's check out 3 pi over 2. Well, cosecant of 3 pi over 2 minus cotangent of 3 pi over 2, is that equal to 1? Well, cosecant of 3 pi over 2, that's negative 1. Using that unit circle, minus cotangent of 3 pi over 2, that's 0. So is negative 1 minus 0 equal to 1? No, that does not work out. So you have to come over here and label this as extraneous. If you don't label it extraneous, then you haven't removed it as a solution. And that means your entire solution, even if you've done all this work, is incorrect. So you do have to remove it, or else your solution's not right. And I've pretty much answered this question on the last problem of what must you be careful of when you square both sides of an equation in the process of solving the equation. And the answer to this is you could possibly end up with extraneous solutions. So extraneous solutions is what we're looking for here. So in order to avoid extraneous solutions, you have to check each of your solutions. Now let's see if this is going to be correct. We'll explain if it is or if it's not, and then we'll see what happens. So let's see. There's all this work, and then sine of theta plus cosine theta is equal to 1. So it looks like they squared both sides. So sine squared plus 2 sine theta cosine theta plus cosine squared theta is equal to 1. That looks like it works out. And then sine squared theta plus cosine squared theta, well, it looks like there's actually two steps happening here, because that's equal to 1, but then they subtracted 1 on each side, and 1 minus 1 is 0, so that's where that 0 is coming from. And then I had 2 sine theta times cosine theta divided by 2. Okay, so that makes sense. We divided by 2 right there. And I'm left with sine theta times cosine theta. And then we just use the zero product property. So sine of theta is equal to 0, or cosine theta is equal to 0. One of those is going to have to match up. Well, what I said on the very last problem was whenever you square both sides of an equation, you could end up with extraneous solutions. So we need to come up and check each of those solutions. So I'm going to use orange this time to check. So sine of 0 plus cosine of 0, is that equal to 1? Well, sine of 0, that's 0, plus cosine of 0, that's 1. Does that equal 1? Yeah, that checks out. And then pi, we need to check pi. So sine of pi plus cosine of pi, does that equal to be 1? Well, sine of pi is 0, but cosine of pi is negative 1. So I have minus 1. Is that equal to 1? No, that is not a true statement. This one is extraneous. So I now know that the following solutions aren't correct because it looks like I have extraneous solutions. Well, 0 was good. Let me check these other two. Sine of pi over 2 plus cosine of pi over 2, is that equal to 1? Well, sine of pi over 2 is 1, and cosine of pi over 2 is 0. Well, 1 plus 0 is 1, so that works out. Well, maybe 3 pi over 2 won't work out, so let's check that. Sine of 3 pi over 2 plus cosine of 3 pi over 2, is that going to be equal to 1? Well, sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. Well, negative 1 plus 0 does not equal 1. So again, we have another extraneous solutions. So the correct solutions are only theta is equal to 0 or theta is equal to pi over 2. We did not want to include pi and 3 pi over 2 because we've squared both sides, and we always need to check our solutions when we square both sides. All right, so that is going to wrap up the review. I hope you have no problems with this test. If you're worried about it, come in the morning or in the afternoon so we can talk about this. Don't forget, you're always going to have retests the following week. But if you have any questions, you just let me know. I'm Mr. Hernandez, and I'm always here to help.